Here's section 5.3, and this is kind of the geometry, or at least a little bit of the geometry of complex numbers. And the idea here is that they're getting for us is that you put the, here's where we do X and here's where we do Y, similarly, right? But this is the real axis and this is the imaginary then. And so the idea is that, for instance, if I plot, Z equal X plus IY, then I would go out here some, well, let's call it X0, Y0. So I go out here X0, go up here Y0 maybe if those were two positive numbers, and there would be a point associated with that Z, or we could think of it as that vector from Z. And in which case, then when I add two, if I take a Z1 plus a Z2, then the geometry is that, say, there's Z1, and if, let's put Z2 right like that. Ooh, it made a straight line. I don't know how I did that, pushed a button somehow. But anyway, there's a Z2. Then if I want to look at Z1 plus Z2, I can just geometrically add them by, moving this complex vector, its tail to the head of that one. So there's Z2. And so then that spot is Z1 plus Z2. I'll get rid of that. Whoops, not what I wanted to get rid of, but hey, I can put it back. Okay. So they're looking at that sort of thing. If I do a subtraction, I don't know if they talk about subtraction in there or not. Yeah, I guess. Oh yeah, they have a subtraction, and so if I did a Z1 minus Z2, okay, well, this is equal to some Z, then kind of the way I end up looking at this is that, I'd say Z1 plus what is equal to Z2. That's how that helps me draw it. And so here is the Z1 again, that same Z1. And here is the same Z2 in its correct spot. There's Z2. And then, see, so this vector is Z1 minus Z2. I connect the heads, and the tail of the answer started at the Z1, the thing that was subtracting Z2, ended at Z2. But, how did that work? Well, I added Z1 plus this vector to get to Z2. So that's kind of geometrically how I come up with Z1 minus Z2, something like that. Okay. And now some other things, I've mentioned the conjugate. So if Z is X plus IY, then the conjugate of Z is X minus IY. And so again, if I were to draw these things, all right, so maybe that's Z, then Z conjugate would be the mirror image across the real axis. So here's Z bar. Okay. And, I could, well, let's go a little further. Let's look at some particular things. You know, here is the number 1. If I go up 1 unit this way, so here's x, here's y. Here is the number I. And here is -1. And down here is -I. Okay, so if I, you know, if z is equal to I, it goes right there. Okay. And I think that is pretty much all they really had in this section. Let's see. They've got the half plane. They've got oh, they mention a line through 2 distinct points. So let's look at that. That's probably the only other thing they have in there. So, you know, here's a point, and that is made from a particular, say, Z1. And, you know, here's another point made from some Z2. And if you wanted to talk about the line that goes through there, you know, how could you talk about that? And well, what you use is what looks kind of like a convex combination of things. So say I wanted to start at Z1 and end at Z2 and just do that much of the line. Well, what I could do is parameterize it and say 1 minus t times Z1 plus t times Z2. And notice that when t equals 0, I get Z1. When t equals 1, I get Z2. Now, if t is between 0 and 1, I'll get a point in between somewhere. And if t is outside of 0 and 1, I will get points out here. But that's a nice way to create the line. And then if we did it by components, you see this is 1 minus t times x1 plus I y1, and then plus t times x2 plus I y2. And so if I did it by each component, you know, a given x would be 1 minus t times x1 plus t x2. And a given y, now I won't have the i's in here because I'm just looking at the imaginary part, just the real number that goes there. Then this would be 1 minus ty1 plus ty2. Okay, and so that's a nice way to describe a line, say, joining these 2 points in the complex plane. Alrighty, and I think that is 5.3.